Come on. Live, and I'm live. Excellent. Okay. First, we're still in the first marking period. You had a major due for me at the end of last week. I gave you a lot of time to get that thing done. There's still some people who haven't gotten that done. If you haven't gotten it done, it is now considered late. You need to get that thing into me. The link is on Google Classroom for Edge Elastic. Make sure you're jumping on that. Otherwise, guys, we're coming to the end of the first marking period, and if you haven't made stuff up for me, you need to make stuff up for me. I came in this morning, and I had about 100 emails because I didn't check my email much over break. I started checking it a little bit yesterday, and I started checking a bunch this morning, and out of those 100 or so emails, I've only gotten through about half of them. So if you did message me over break or recently in the past few days, I'm working my way towards your emails, so please keep that in mind. But the first marking period is coming to a close. We're still in the first marking period. Closes about the 12th or 13th. I'm stuck in my wire. There we go. And then next week begins the beginning of the second marking period. Oh, so fun. And who the heck knows what form that would take. Excitement fills the air. But yes, make sure you are jumping on top of the stuff that you owe me because that marking period grade is going to impact the rest of the year, of course. This year, believe it or not, as crazy as this calendar year has been, it has kind of flown by. Because if you think about it, we're almost to the middle of November. And you think about it like, okay, December, January, February, March, well, one full year since this whole thing happened. What crazy times we live in. Anyway, what we're doing today. Today, I'm going to be introducing to you the next unit that we will be starting. The next unit is going to be utilizing some skills that we have learned in past chapters. So please keep that in mind. The stuff that we have learned in past chapters are coming back in a big way. But I am going to be taking it to another level. So if you would, I'm not going to waste much time with that. I'm going to need those notebooks out and open. Let's see. There we go. Okay. So now as you're setting up those notebooks for me, because there's going to be a lot of information that you're going to have to write down today, I wanted to remind you of what we've done in the past. What's on the board right now from Desmos is a quadratic. We've seen this quadratic before. We can do various things with this quadratic. We can describe a vertex of this quadratic. We can find the x-intercepts of this quadratic. We can recognize it to be a parabolic shape. It is symmetric. It is opening up. There are a lot of different things that we can say about this quadratic. But the thing that I want to point out to you more than anything else is that this quadratic is what we call a second degree polynomial. We call it a second degree polynomial because of the largest exponent that is on there. The largest exponent that is on there is a 2, so it is a second degree polynomial. Polynomials are basically equations that have exponents, but those exponents are whole numbers. They're whole positive numbers. Now, obviously, if we went to negative numbers, that'd be a different story. That's another chapter. If we went to fractional exponents, that's a different chapter. I'm sticking with whole numbers for now. But the thing that I wanted to bring your attention to is, well, what would happen if I changed this particular equation from this simple quadratic second-degree polynomial to something like this? Make sure I type this in correctly. Boom. And let me get rid of that 4. Yeah, let me make that a -3. Oh, that's nice. There we go. Look at that. Look at that junk right there. Now, this is a good example of a third-degree polynomial. This is a good visual example of a third-degree polynomial. A third-degree polynomial doesn't necessarily always have this exact shape, but it is a good example of one. We can describe many things about this third-degree polynomial. We can say that it only crosses the x-axis once. You can see that the red line only crosses our x-axis once. I could say, well, it has this weird kind of curvy thing right in the middle there. To the left, this thing seemingly goes down forever. And to the right, this thing seemingly goes up forever. This is completely different from a quadratic. With a quadratic, you either had a polynomial that opened up like that, or opened down like that, some weird junk like that. But now we have this thing doing twisty turns in the middle. What in the heck is going on here? I'm going to change one more thing on this one. Let's see. Nope, move it down. There we go. Look at that one. Look at this one. This thing crosses the x-axis 3 times. 3 times. If I was talking about solutions, if I was talking about x-intercepts, it would have 3 different solutions. This thing is insane. I could go crazier. I could go even crazier with this one. Let's see. I could do x to the 4th power. Let's see, minus 16. No, I don't want to do 16. Let's do that one. Let's do plus 7x squared plus 3x minus 9. I do make that a 2. No, make that a. I want to put something else in here. Let's make that a 3 here. Oh my gosh, look at that. Look at that. Look at that weird thing. I'm going to zoom out. Look at this weird thing. I'm gonna exemplify what this thing actually does in a moment. Check this out. So this thing seemingly just comes straight down like this. It seemingly comes straight down like this, and then comes to like a little tip right here, and then it comes all the way back up. And then it seems like, oh, okay, but then it does this weird kind of wiggly thing right here. And then it goes back out like that. That is literally what the graph does. It is messed up. Eventually, we're going to get to a point where we can graph these things. But I want to go a little bit simpler. I want to go a little bit simpler with these things. These graphs can do so many different things that you're probably not very comfortable with. I have seen graphs do all sorts of wiggly things right in the middle. See if I can't get one to do that, actually. I think I can, actually. Hold on. Let's try this. Let's try minus x squared plus 1. Oh, yeah, look at that. Look at that. Look at this graph. Look at this graph. But this is what we're going to be dealing with. This is the type of graphs that we're going to be dealing with. So, in our notes, let's start off very simply with this. Let me give you a definition, and then let me show you what we can do with them. So first and foremost, I'm just going to call this Intro to Polynomials. Today is the 9th. Make sure we are writing these things down, ladies and gentlemen. I don't care that it's November. I'm going to be going full steam ahead the rest of the year. Let's start off with something basic like this. A polynomial is an equation where all exponents are positive whole numbers. I want to specify this because I want you to be able to recognize what the heck is going on here. A polynomial is an equation where all of the exponents are positive whole numbers. Here are a few key examples. I could say y equals x squared plus x minus 6. This is your basic quadratic that we've been dealing with. All of the exponents are positive whole numbers. For example, just for the sake of argument, this x right here technically has an exponent of 1. Positive whole number. No fractions, no negative exponents. Now, I want to specify no negative exponents. You can have negative numbers, you just can't have negative exponents. Here's another example. X to the third power plus x squared minus 3x plus 7. That is an example of a polynomial. Again, all positive whole numbers in the exponents. Something very basic, y equals 2x plus 1. That is a linear equation. That's linear. But it is a polynomial. It is a polynomial. Please keep that in mind. Everything that we've been dealing with, linear equations, quadratic equations, they are polynomials. They just have a very specific definition to them. Linear, quadratic, they all fall under polynomials. You guys, not to bring up a PTSD moment, but you know the word polygon, right? You know polygon, squares, rectangles, those are all quadrilaterals, triangles, pentagons, octagons. They're all different shapes, but they're all polygons. These are all polynomials in the same vein. Let me try something here. I'm going to show you something. Let's say f of x equals, let's do that one, yeah. 3x cubed minus 4x squared minus 17x plus 6. Let's just say that that was our example right there. Give me a small number that's not 1. 3, okay. Now check this out. Let's say that I wanted to evaluate this polynomial at x equals 3. I wanted to evaluate this polynomial at x equals 3. So if I wanted to do that, let's say evaluate f of 3. If I wanted to do that, I could take that 3, I could plug it in for all of the x's, and I'll do this for you in a moment. I have no idea what this number is going to end up being. Let's just see what happens. But if I was to evaluate it at f of 3, I would plug a 3 in for all of the x values, and I would go about attempting to evaluate it like this on my calculator. And you can see me typing that thing in. I'm just double checking to make sure all the numbers are correct. Chapow! Oh, wow, you hit the perfect number. You know why? What did I get? What did I get? Oh, trying to zoom in more. Yeah, I got 0. I was not expecting that. I was totally not expecting that. Because you picked the number. Well, let me focus this thing a little bit more. But we got 0. Holy crap, we got 0. Now what that means for us is f of 3 is equal to 0. Or 3, 0 is a point on the graph. There's a lot of different things that we can tell as a result of this. We wanted to evaluate f of 3. Miraculously, we got 0. It tells me that the input 3 produces an output 0. 3, 0 is a point on that graph. Let me take a look at Desmos. I'm going to put this equation into Desmos just because I want to see what happens with this. I want to put this equation into Desmos just for funsies. Let's see. x to the third. Oh, I'm sorry. It was 3x to the third minus 4x squared minus 17x plus 6. Let me zoom out a little. Look at that junky thing right there. That's amazing. That is amazing right there. So check that out. Look at the point that I just highlighted. I don't know if you guys can see this in the chat. It might be a little bit more difficult. No, you can see it a little bit in the chat. Anyway, this graph, which does this weird thing right here, has 3, 0 as one of its solutions. Has 3, 0 as an x-intercept. Now, I wasn't expecting that whatsoever. I really was just expecting some other number to come up. But I just said a small number because I knew the answer would be between like -20 and +20. I'm going to show you a magic trick. I'm going to show you a magic trick that I don't know if you have ever seen. A mathematical magic trick. Back in the day, just as a quick question for myself, were you guys ever taught lattice multiplication? You were. You weren't. I guess it depends maybe. Did it depend on the elementary school teacher you had? I don't know, maybe. I don't know. I'm not a fan of lattice multiplication. I'm not. But there is a very specific type of multiplication that I want to show you. It's a different type of multiplication. It's a different type of mathematical computation that I need you to be familiar with, because this mathematical computation, if you can get this down, will determine how well you do the rest of this chapter. Oh my goodness. Let's try it. Let me show you what it looks like. And then I'm going to show you how it works. So please copy this down. I'm going to make an L, but in like an elongated L kind of thing. This is the first time you're seeing this in my classroom. I don't know if you've seen it in other classrooms. I'm going to write some numbers across the top. Now, those numbers did not come from nowhere. Those numbers belong to the equation that I have at the top of the board. Those numbers, 3, -4, -17, 6, they are the coefficients from the equation that I wrote at the top of this board. I'm still sticking with the same exact equation. I'm not leaving it behind just yet. And on the outside, I'm going to put the number that she chose for me to plug in. She told me to plug in a 3. Now check this out. I'm going to show, again, this is going to be a little weird. It's going to be a little weird, but I need you to see how this works. I need you to see how this works. I am about to do a sequence of addition and multiplication, addition, multiplication, addition, multiplication. I'm going to keep doing that back and forth until I get to the end. I'm about to do a sequence of addition, multiplication, addition, multiplication. I need you to see how this works, because this is going to influence a lot of stuff that we do. A lot of stuff that we do. Here we go. First of all, this 3 that I'm pointing to, this first number that I'm pointing to, I'm going to add it to what's directly below it, which is nothing. So 3 plus nothing is just 3. Yay, happy day. Oh, fantastic, cool, okay. Then I'm going to transition to multiplication. But what am I going to multiply it by? I'm going to multiply this 3, the one that I'm pointing to. I'm going to multiply this 3 right there by the number that's on the outside. 3 times 3 gives you 9. Good for me. It gives me a 9. And I'm going to write that 9 in that first blank space. Look where I wrote it. Let's argue, where'd that 9 come from? That 9 came from when I multiplied 3 plus 3. Now remember, I'm going to go back and forth between addition, multiplication, addition, multiplication. So I started by taking this 3 and adding it to nothing. And then I took the result and I multiplied it by this other 3. Now it's time to go back to addition. -4 plus 9 is 5. I added those two numbers together vertically. Then I'm going to go back to multiplication. And I'll go over this again when we're done. But I'm going to multiply by this 3 again. This 3 on the outside is what I always multiply by. 3 times 5 would give you 15, which I'm going to put that 15 right here. Then I'm going to go back to addition. Adding those two numbers together vertically gives you a -2. Then I'm going to go back to multiplication, in which again I multiply by this number on the outside. -2 times 3 gives me a -6. Finally, I'm going to go back to addition, where I add these two numbers together and I get 0. Now, there are two very important things that I want to talk about. Number one, I just want to go over the synthetic, well, I haven't actually called it that yet, but I will. I want to go over what I just did. That's number one. And then number two, I want to show you the consequences of what you just did, because this is so important. First, these numbers right here, 3, -4, -17, 6, they came from, oh no, I'm stepping on stuff. They came from the original equation at the top of the page. They came from that original equation at the top of the page. They are the coefficients. It is a 3x cubed minus 4x squared minus 17x plus 6. You only put the numbers, not the variables. Then, what number am I plugging in? If the number that I'm plugging in, if I know what it is, I'm going to put that number right there on the outside. That's the setup. This process is nothing more than addition, multiplication, addition, multiplication. It just goes back and forth and back and forth. 3 plus nothing. 3 times 3. The result goes in that blank spot. -4 plus 9 gives you 5. 5 times this 3 again gives you 15. Adding vertically, -17 plus 15 gives you -2. Multiply by that 3 again to get -6. Add vertically to get 0. I want you to label something. I want you to label something here. I'm going to zoom in on this. I want you to label something. This is the number you plug in. This is the number that you plug in. This is the number you get back. That number on the outside of this bar is the number that you're plugging in. The number at the very end is the number that you get back. It may seem ridiculous to do, like, what, Ms. Rankin, we have the answer from up top. I know we have the answer from up top, but this bar is going to be one of the most important things you see in this unit. Let me repeat what I just said because I need you to hear that. This process, this bar, is going to be one of the most important things that you see in this unit. Trust me on that. So what this is called synthetic substitution. Let me write this down. Synthetic substitution. I'm also going to refer to it by a different name later on, but this is referred to as synthetic substitution. We can plug in any number we want. Let me try an example here. Let's try a different example. Let's try f of x equals x to the 4th minus 2x squared plus x minus 1. I did not make a typo. Let me repeat. I did not make a typo. Give me a number, any number. Doesn't matter what it is. Make it single digit, though. Positive or negative, I don't care. Give me a number. -4. Let's do it. No, we'll do it two ways. We'll do it two ways. First, we'll do this by plugging in the -4. Now, my use of parentheses is on purpose. My use of parentheses is important. Please make sure that is written down correctly. I'm going to go to my calculator. I'm going to very carefully type this thing in. Let's see. -4 to the 4th minus 2 parentheses -4 to the 2nd plus parentheses -4 minus 1. Chapow! 219. 219. Okay, that's cool. Good for it. Fantastic. Sometimes it can be that simple to do it. But again, I want to use synthetic substitution. This, what I just did, is actually referred to as direct substitution, but I want to do synthetic substitution. This bar is known as the synthetic bar. That is what that bar is. That -4 is the number that I'm plugging in. So that number that I'm plugging in is going on the outside of that bar. Tell me, what's the first number I write on the inside of this? Definitely a 1. Definitely a 1. Even though there's no number there, you assume it's a 1x to the 4th. Absolutely, yes. You assume it's a 1x to the 4th. Now, I'm being very deliberate with my delivery right now. I'm being very, very deliberate with my delivery right now. I start off with a 1 on the inside because that's the coefficient. What number comes next? Oh, no, it's not. It's not. Now, 99% of people would say -2. 99% of people would say -2. Unfortunately, it's not -2. Ladies and gentlemen, on the inside of that bar, I have to write the coefficients, just like I did last time. Last time, I wrote the coefficients on the inside of that bar. Oh, happy day. Yes, the first number that I'm writing is a 1 because it's a 1x to the 4th. Yes, that is exactly what I'm going to do. The second number that I'm going to write is not going to be a -2, however. Because, tell me, what is the largest exponent in this polynomial? 4. The largest exponent is a 4. It's definitely a 4. After the x to the 4th should be an x to what power? It should go x to the 4th, x to the 3rd. There's no x to the 3rd in this polynomial. Look at it, look at it, look at it. They have an x to the 4th. They have an x to the 2nd. They have an x to the 1st. And then they have a constant at the end. There's no x to the 3rd power. There is no x to the 3rd power. Guess what you got to do? Watch what I'm going to do. You have to account for it. You have to account for that missing term. You have to. If you do not account for that missing term in the polynomial, then everything will be screwed up. Everything. Everything. The remaining numbers look like this. -2, +1, -1. Because it is a 1x to the 4th, that x cubed is missing, so you have to account for it with a 0. It is a -2x squared. It is a +1x, and then a -1 at the end. You put the coefficients in there. You need that 0 there. If you don't have that 0 in as a placeholder, it's gonna spell disaster. Let's do the synthetic. I'm going to start by adding this 1 to nothing. The 1 just drops down per the usual. By the way, I'm going to go through this slowly, but if you want to skip ahead and actually show that you did it correctly, go ahead, do it. Go rush through it. You should, if you got it right, you got it right, but let's see what happens. After I add 1 to nothing, I get 1. I multiply by the -4. Then I add vertically. Then I multiply by the -4. Then I add vertically. Then I multiply by the -4. Then I add vertically. Then I multiply by the -4. Then I add vertically. Again, this is what I'm saying about the back and forth and back and forth. This is why I deliberately explained it like that. It's nothing more than adding vertically and then multiplying by the number that's on the outside. This is the number that you're plugging in. This is the number that you're getting back. Question, 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 question. Because I don't know the answer to this. When you guys learned division in like, I don't know what grade you were in, maybe like what, 4th or 5th grade? I have no idea what grade you learned division in. Did you learn long division? You did. Is there an alternate version? I don't know. I've seen people do really weird alternate versions with like long division where it's like they write numbers like on a column along the side on the outside or some junk like that. I don't know. We're going to get into those details. Ms. Markey, why are you bringing up division? I don't know. Maybe there's a reason. Maybe there's a reason. But let me wrap up this particular problem. So, for example, the number that you plug in, there's the number that you plug in. Make sure you're writing this down, equals the number that you get back. That is what those two numbers are for. What about the rest of the junk? Well, we'll get there. We'll get there. But I just wanted to show you how the synthetic bar works. This is called synthetic substitution. The number that you plug in is on the outside on the far left. The number that you get back is that bottom right number. You need to make sure it's done correctly. Now, I'm about to show you something here. I'm about to take this a step farther. We're still going to be using the synthetic bar. Whoa, that's a buzzing. We're still going to be using the synthetic bar. Oh, but we're going to be taking it farther. Let's see what happens here. Let me start with a basic thing like this. Example, let's say x squared plus 7x plus 12. Yes, let's do that. I should say like y equals or f of x equals or some junk like that. There we go. Let's start with that. A very basic quadratic. A very basic quadratic that we have been doing. Now, this quadratic dates back so many months to the beginning of the year since we've been working on this information. We'll deal with that in a minute. Let me look at this quadratic in Desmos. Let me look at this quadratic in Desmos. X squared plus 7x plus 12. I keep putting equal signs. There we go. Zooming in, zooming in, zooming in, zooming in, zooming in. Look at that. There's the quadratic in Desmos. Zoom back out. There we go. Now, there's a couple things you need to know about this quadratic in Desmos. I just highlighted it right there. The two things that you really should be focused on with this quadratic is where are the zeros? The zeros of the function. In this case, my zeros are at -3 and -4. Now, that's interesting. To me, it's interesting because if I take a -3, if I take a -3 and I take that -3 and I plug it into the equation, it should result in a zero of the function. And that actually is a definition that I want to give you. Hold on. Hold on, I gotta get this. There we go. Where'd my thing go? There it is. There we go. Let's try it. So, we believe -3 is a, quote, zero of the function. We believe -3 is a zero of the function. Let's try it. -3, synthetic bar, 1, 7, 12. We believe that -3 is a zero of the function. Again, I put that word zero in quotations right there. Now, if we're correct, then we can see what happens with this synthetic division. Multiply, add, multiply, add. Yep, absolutely, yes it is. F of -3 equals 0. F of -3 equals 0. This number seems important. Or these two numbers right here seem important. I guess we'll come back to that another time. So again, let's just give you a little definition right here. If f of k equals 0, then k is a, quote, zero of the function. Here's the definition that I just want to give you right there. We've been talking about this for quite some time, but I just want to give you this definition. If f of k, whatever that k is equal to 0, then k is what we call a zero of the function. Now, this comes into play for a lot of different things. A lot of different things. Let me try one of these weird things right here. Let's try a slightly different example. Let's try a slightly different example and see if it kind of plays out the same way. Let's try f of x equals, see if this one works, x to the third power minus 6x squared plus 13x minus 10. There we go. Now, here's going to be the beauty of the whole thing. If I ask you to find the zeros of an equation like this, you may end up guessing for quite some time. But because of the graphing calculators that you all have on the Chromebooks, because of the technological advantages that you have, you can do something like this, where I can go back to Desmos. I can type in the equation that we're dealing with. There we go. I can kind of zoom in right there just to kind of see what we got there. Oh, did I type that in right? No, I didn't type it in right. Look right here. Boom, that should be a minus sign. There we go, much better. What do you think the zero of the function is? If you had to visually identify it, what's the zero of the function according to my graph? What's my zero? What's my x-intercept? What's my solution? 2. It looks like 2. Now, should I trust the computer? Maybe. I don't know. I don't trust computers. But it looks like 2. It seems as if 2 is a zero of this function. Let's prove it. If you want to prove that 2 is a zero of this function, let's do synthetic division or synthetic substitution. So Take a moment. Take literally the next 30 seconds or less. You do it. You fill out this synthetic bar. You fill out the synthetic bar and you prove that it is a zero of the function. I'm just going to go very slowly while you guys rush to the end to prove it. I'm going to go very slowly with this, filling in the appropriate numbers. Once you get the hang of this, it's the quickest thing in the world. It's the quickest, it feels like the quickest thing in the world. Multiplication, addition, multiplication, addition, multiplication, addition. And I get down to that. I have just shown, by the way, it took me about 45 seconds to a minute to write all that out. But this proves x equals 2 is a zero of the equation, or of the function, I should say. Let me zoom in on that. This zero, this resulting zero, proves that x equals 2 is a zero of the function. It's what it does. It's a really messed up looking graph. It's a really messed up looking equation, but that's exactly what it does. It's so amazing. So amazing. All right. I want to make up an equation that ends up working exactly the way that I want it to. Let's try that one. So that would be that and that and that times that. You can't see it right now, but I'm making up an equation that I want to make sure works exactly the way that I want it to. Got him. Okay. We're about to take this up to another level. We're about to take this up to another level. Let me give you a little definition here. People in my hallway. I'm going to give you another definition here. Let me give you this little bullet point there. There we go. If f of k equals 0. Now, we just showed before that if f of k is equal to 0, then k is the 0 of the function. But I want to go one step farther. If f of k is equal to 0, then x minus k is a factor of f of x. We just said before that if f of k is equal to 0, then k is a 0 of the function. But I want to go a step farther and show you that if f of k is equal to 0, then x minus k is what we deem to be a factor of f of x. This is going to be amazing, what we're about to see here. Check out this example. This example we're going to be focusing a lot of our attention on for the remainder of the class period. F of x equals x cubed plus 2x squared minus 5x minus 6. We're going to be focusing a lot of our attention on this particular polynomial, because here is my ultimate goal with this polynomial, this exact one that you have written on the board right now. With this polynomial, we are not just going to find the zeros. We are not just going to look at the graph. We are going to factor it completely. We are going to dissect this polynomial into its individual pieces. We are going to break this thing down step by step using synthetic substitution. Now, in the previous chapter, ladies and gentlemen, in the previous chapter, I taught you the Tucker method of substitution. And a lot of people decided, I don't need the Tucker method of substitution. I'm just going to use whatever photo math is out there. Okay, that's cool. Let's see how that works out for you. Because then you did your photo math and then you didn't do well on my assessments. That didn't work out too well. I wonder if it's easier to learn what Mr. Markey's teaching. Yeah, it is. It's much easier to learn what I'm teaching. Oh no, my cord. I did it again. We're going to break this thing down piece by piece. It's going to be fantastic. First, let's take a look at the graph. If I looked at the graph of this thing, let me change this up. This was a plus 2x squared minus 5x minus 6. There we go. Look at this thing. Look at this thing in all of its wonderful glory. That is the graph. Now, I'm not worried about the graph right now, but what I am worried about are the possible zeros of the function. The possible zeros of the function. I highlighted them right there. I highlighted them. I don't know if you can see them. I mean, they're kind of smallish thing, but I have 3 zeros of the function. Positive 2, negative 1, negative 3. Now, let me just make a little note here. From Desmos, we see 2, negative 1, negative 3 as zeros of the function. I'm going to be focusing a lot on this polynomial. You can't see what I just wrote. There it is. From Desmos, we see 2, negative 1, and negative 3 as zeros of the function. And I'm about to break this thing down piece by piece. Check this junk out. Now, what this means in terms of the definition that we just did, this implies x minus 2, x plus 1, and x plus 3 are factors. I'll give you a moment to kind of look at that. I want to explain this in a little bit more detail. According to the definition that I just gave you at the top of the page, we see that 2, negative 1, and negative 3 are what we call zeros of the function. This implies that x minus 2, x plus 1, and x plus 3 are what we call factors. And yes, that is absolutely true. That is absolutely true. Now, there are many ways that we can prove this. We're going to break this thing down piece by piece. You're going to see how we're going to break this thing down. Now, in a moment, I'm going to show you something remarkable on my graphing calculator. In a moment, I'm going to show you something absolutely remarkable on my graphing calculator using this example, using these factors. Watch what's about to happen. It's going to be insane. First, let me reset that. There we go. Let me type in the equation. First, x to the third plus 2x squared minus 5x minus 6. Let me zoom in on my graphing calculator. Ladies and gentlemen, I want you to see what's going on here. Let me focus the screen. There we go. I need you to see what's going on with this thing because this is absolutely phenomenal. Graph. Now, first of all, here's the graph that we've seen in the past. There it is. Yay, we saw that on Desmos. No big deal. We saw that on Desmos. Trace. I could type in the number 2. You could see it blinking right there on my screen. 2, 0 is a x-intercept. It is a 0 of the function. Oh, happy day. Now, watch what's about to happen here. I'm going to take that polynomial and I'm going to divide it by x minus 2. I'm going to divide it. Let me ask you a question. Give me a factor of the number 48. Give me a factor of the number 48. What number divides 48? Oh, come on, high school students. What's the easiest number that can divide 48 that's not a 1? Yay, we did it! Yay! Okay. You could take 48 and you can divide it by a factor. And you're left with 24. Now, 24 is also a factor, but that factor can be broken down even farther. You guys have done factor trees way, way back in the day. You can do something with like 48, and then you're like, I'm going to break it down to 24 and 2, and then you can go farther if you wanted to. But that's not the point. My point is this. If you divide by a factor, you're going to get something absolutely remarkable. Watch what's about to happen on my screen. Watch what's about to happen on my screen, because I just took that cubic, that third degree polynomial, and I'm going to divide it by a factor. Look what just happened. Look what just happened. This. We need to recognize what the heck's happening here. Look at this. First, let's go back to the y equals k. This was a third degree polynomial. Let me look again. Here's what the third degree polynomial looked like. Let's just look at the third degree polynomial one more time. Look at this crazy, wacky thing. I'm going to trace this on the board, actually. Hold on. This thing, I'm going to trace this because it's going to go away in a moment. I'm going to trace this so you can see what's going on here. And we know what those 3 zeros are. Then I decided to divide by x minus 2. Watch what's about to happen here. I decided to divide by this one. We divided by x minus 2. We got rid of that 0. Ladies and gentlemen, watch what's going to happen. Watch what's going to happen when I hit graph on this one. First of all, first question. What shape is this resulting graph? What shape is that? What type of equation is that? Oh, ladies and gentlemen, this is the most important thing you're going to see in your lives. What's resulting is a quadratic. What's resulting as a quadratic is a parabola. But more importantly, the resulting parabola has the exact same zeros of the other equation. We just divided by x minus 2. We got rid of that. We divided it out. But then we resulted in this quadratic. Let me divide it again. Let me divide it again. And let me just see what happens here. Hold on. Let me divide it again. But this time, I'm going to divide by x plus 1. I'm going to divide by x plus 1. I'm going to divide and get rid of this one right here. We're going to divide by the x plus 1 factor. Let's just see what happens to the graph. What is resulting is a straight line, a linear equation. A linear equation that just so happens to have the exact same 0, the only 0 that we did not divide by. Everything that you have been doing is absolutely connected into one unified thing. I need you to see that. So hold on. Let's go back. Let's to our notes. And let me write some important stuff here so that we have this written down. Nope. There we go. Zoom back out. So first of all, just to recap a couple things. X minus 2, x plus 1, x plus 3 multiplied together give you x cubed plus 2x squared minus 5x minus 6. Those things multiplied together give you the cubic that we have been dealing with. There we go. Oh, I totally missed. How did that bounce back? Whatever, don't care. Multiplied together give you that cubic equation. If we divide x cubed plus 2x squared minus 5x minus 6, if we divide it by x minus 2, I'm going to tell you it results in the following: x squared plus 4x plus 3, which is equal to x plus 1, x plus 3. Division is a tricky thing. Division is a tricky thing. Let's go back to our synthetic bar. Watch what I'm about to do. Because I need you to see how these things are connected. This is an unbelievable portion of this chapter. Now, first of all, this right here is the zero of the function, x minus 2 is a factor, but I put that zero of the function that I'm dividing by on the outside. As I said, we were going to spend the remainder of the class period on this one equation. I'm going to rock out a quick synthetic substitution here. This proves x equals 2 is a 0, as we did in the past. But there's something more important going on here. There's something more important going on here, ladies and gentlemen. I need you to see this very clearly. This bar is not just a substitution bar. This bar is going to be the bar that we are going to use to divide polynomials. We are going to divide polynomials. And not only does this substitute or this synthetic bar divide polynomials, taking this cubic equation, this 1x cubed plus 2x squared minus 5x minus 6, and we're dividing it by x minus 2 as its factor, proving that it is a 0 of the function. But look at these numbers right here. Look at these numbers, these three numbers, this 1, this 4, and this 3. Look at the 1, 4, and the 3. And look what you have up here. Look at what I'm pointing to. Look at this quadratic that I'm pointing to. And look at these three numbers right here. That is not a coincidence. This is not a coincidence, ladies and gentlemen, at all. You've actually just performed your first step of what we call synthetic division. Synthetic division is going to be one of the most important concepts that you see in this chapter. It is going to be one of the most important because it is going to allow you to break down polynomials more than you ever thought you could. Hold on. So let me show you what this problem would look like. Let me show you what this problem would look like if you had to do it for, let's say, a homework or an assessment. I might give you the following example, and I'm going to walk you through exactly exactly what you should be doing. So I might give you the problem that says factor completely x cubed plus 2x squared minus 5x minus 6. Now, yes, it's the exact same problem, but I want you to see exactly how I'm going to do this. This is exactly what I would expect on an assessment of mine. So I'm faced with this cubic. Now, I don't have to graph it. I don't have to solve it. They want me to factor completely. The Tucker method doesn't apply to cubics. I can't do the Tucker method here. Some people tried to pawn off a version of factoring called grouping. Here's the fun fact. Grouping doesn't work on this polynomial. Grouping does not work here. You have to go a bit deeper. So what I would do if I was faced with this polynomial, the very first thing I would do, the absolute first thing I would do would be to look at the graph. And I would look at the graph and I would say, well, that's messed up. But it looks like 2 is a 0 of this function. It looks like 2. All right. I guess it looks like 2. So let me do this. And again, I know I'm doing the same exact problem. I don't care. I want to do it this way to show you exactly what is expected of you. And I would run through this synthetic division exactly as the way that I've done before. But now I'm going to take it slightly different. This 2 is a 0 of the function. And by the definition I gave you earlier on a bullet point, that shows me that x minus 2 is a factor. But now let's look here. I've been saying that this is division. Division, division, division. This number right here represents the remainder. It represents the remainder of your division. When you divide things, sometimes there is a remainder if something doesn't divide evenly. But if you don't have a remainder, that remainder is 0. In this case, that's exactly what we have. We have a remainder of 0. Good. That's what we needed. This number is your new constant. This number is your x term. This number is your x squared term. After the remainder, you have a new equation. After the remainder, you have a new equation that you can deal with. And that new equation is 1x squared plus 4x plus 3. That is your new equation. Well, we just spent the last 2 months factoring quadratics. We just spent the last 2 months factoring quadratics. I can factor that. It factors into x plus 3, x plus 1. That is what it factors into. I have one additional factor. I have x minus 2 as my additional factor, and that one's just going to come straight down, as we would do with the greatest common factor. This is exactly the type of work that I would expect to see when we are factoring these higher level polynomials. The idea is that we take these higher level polynomials, we break them down as far as we can go, maybe to a quadratic, and once we get it to a quadratic, then we have the option of doing regular factoring using the Tucker method or the quad formula if that comes into play. Ladies and gentlemen, this was a huge introduction. This was a huge introduction to this new unit. The stuff that I have taught you today, I am going to be focusing on for the next several class periods. Keep in mind next week. Next week, if everything goes to plan, I'm going to see you Monday, Wednesday, and Friday. if everything goes to plan. That means New Jersey doesn't shut down. But otherwise, if we do get shut down, I'm still going to be live streaming Monday, Wednesday, and Friday. Now that I do have 2 or 3 days a week with you, I am going to be moving at a slightly faster clip. But like I said, this new concept that I just introduced to you today, I am going to be focusing on it for the next several class periods. We are going to be getting the practice with it because it is that important. Pay attention to Google Classroom. I may be throwing some stuff up there. We'll see what happens. But anyway, we'll see you next time. I almost timed that perfectly. High five, me.